Hey students, welcome back. We're going to start a new chapter today. This is going to be chapter 8. And this is a big one. We're going to learn about a new class of groups called permutation groups. And this is a very important class of groups, right? Cyclic groups were the first class that we learned. Now we're going to study what are called permutation groups. So let's start with the definition. So a permutation of a set capital A is a bijection, say sigma, from capital A to capital A. So any function that is one-to-one and onto from A to A, we call that a permutation. Now, I'd like to start, let's fix a set capital A, and let's think about the set of all possible permutations. So let's let capital S sub A denote the set of all permutations of capital A. Now, let's see, what do we know? If say sigma and tau are elements of S sub A, so both of them are permutations, then if we look at composition, right, sigma of tau, let's see now, composition of bijections is a bijection, and so sigma of tau is going to be a bijection from A to A also, which means that composition is a binary operation on the set S sub A. We know that composition is associative, so from Math 248, we know that composition is associative. Okay, what else do we need? We need an identity. The mapping, which I'll write using a lowercase I, a little I, from A to A. Defined by little I of little a equals little a for all little a in capital A. This definitely satisfies the property of being an identity, so it satisfies composition sigma of I equals sigma, which equals I of sigma. So little I is the identity in S sub A. The last thing, we need inverses. Since we're working with bijections, each of these functions has an inverse. Finally, for each sigma in S sub A, if sigma is a bijection from A to A, then so if sigma is a bijection from A to A, then sigma inverse, it goes backwards, but that means it goes from A to A. So for each sigma, so we have sigma inverse is in S sub A, and it satisfies exactly the property that we need. So we'll say and sigma of sigma inverse equals the identity function, which is equal to sigma inverse of sigma. Okay, so what we just proved, we'll write this as a theorem. And our theorem will tell us that S sub A is a group under the operation of composition. And so this is going to be theorem 8.1. The set S sub A is a group under operation of composition. One piece of notation, it's understood that we've got an operation in our group, and so we don't need to actually write the symbol for the operation. We will think of it as multiplication. The operation is composition, but we're not going to write the circle. We will use juxtaposition. So we write sigma tau rather than sigma of tau. So in this setting, then, composition, it plays the role of multiplication. It's a generalization of this notion of multiplication. Now, one fact that we're going to need here, so this will be theorem 8.2, and it goes like this. If A and B are sets with the same cardinality, then S sub capital A is isomorphic to S sub capital B. Right? So the group of permutations of set A is going to be exactly the same from an algebraic standpoint as the group of permutations of S sub B. And I just want to sketch the proof of this. And I'll let you check the details. So let's see, we have A and B, they have the same cardinality. What that means is there's a bijection from A to B. So let's let, say, little f from A to B be a bijection. And so now we need a one-to-one correspondence between permutations of the set A and the permutations of the set B. And somehow this function f needs to be the link between the two. And so, so let's say, define, let's say, phi from S sub A to S sub B by, okay, so how is this going to work? Phi of sigma, so sigma is a permutation of A. Phi of sigma, then, it needs to be a permutation of B, and so I need to say what this permutation does to an element little b. And what it's going to be is f of sigma of f inverse of little b for all b in capital B and all sigma in S sub A. And then what you should do is check that phi is an isomorphism. And let me just, this looks like maybe I pulled this formula out of thin air. This really is the formula that should make sense. So let me just kind of draw the picture that motivates the definition of this mapping right here. So here's our set A. And here's my set B. And then we know that we have a function, a bijection between A and B, so from A to B. Okay, now what I need to do, right, I have some sigma, that's a permutation of the set A. And so I need a corresponding permutation over here. That's going to be what we call phi of sigma. Now, okay, so phi of sigma will be a permutation of B, so we need to know what phi of sigma is going to do to B. It's going to take it to some other element in the set. To do that, what I do, so notice the formula, we have F inverse of B. So that says pull back into A, apply sigma. So that element right there will be sigma of F inverse of B. And now put it back. Right, so that element right there is going to be F of sigma of F inverse of B. So it's really not that mysterious of a thing, right? Start with B, pull back, apply sigma, put that element back in B. Right? And so that is what phi of sigma does to little b. So there's the idea. One special case, so the group of permutations of the set 1, 2, 3, all the way up to n, this has special notation, so this is denoted S sub n, and is called the symmetric group on n symbols, or sometimes they'll say n letters. Right, so S sub n. Now, in light of this previous theorem here, we know now that any permutation group where the set consists of exactly n objects is going to be isomorphic to S sub n. So let me say that. So in light of theorem 8.2, if our set A consists of n elements, then S sub A, the group of permutations of the set A, is isomorphic to S sub A. And so you can think of it this way then: the prototype permutation groups of finite sets is S sub n. If you want to know, let me say that better. Everything you need to know about permutation groups of finite sets is contained in studying S sub n. So if we want to understand finite permutation groups of finite sets, all we need to do is study S sub n. And maybe I shouldn't make light of that, right? Studying S sub n, that's actually a big task. So for example, if capital A consists of the elements x, y, and z, right, then S sub A is isomorphic to S sub 3. Right? So now to study finite permutation groups, what we need to do is study study the symmetric groups. Now, one thing to observe, so let's say observation, if we take an element of a symmetric group, so if sigma is an element of S sub n, then, all right, so any function is completely determined by what it does to its domain, right? So then, we can say sigma is determined by its action on its domain, which in this case is the set 1, 2, 3, all the way up to n. Now, since sigma is sigma's 1 to 1, that means so let's say it like this. So since sigma is 1 to 1, we have n choices for sigma of 1. Now, once we've put so once we've decided where we're going to put sigma of 1, now we have n minus 1 choices for sigma of 2. So n minus 1 choices for sigma of 2, n minus 2 choices for sigma of 3, and so on, and down to 1 choice for sigma of n. In other words, that tells us exactly what the order of the symmetric groups are. So conclusion, is that the order of S of n is equal to n factorial. So we want to study the elements of the symmetric groups, and so we want a way to represent the elements. So let's say it like this, representing elements of S of n. So, okay, so let's call it sigma. Let's let sigma be an element of S of n. So what does that mean then? So then sigma is a bijection from the set of numbers 1 through n up to the set of numbers 1 through n. So this is a bijection. And so what I need to do, if I want to tell you how sigma behaves, what it does to each of the elements, sigma of 1, sigma of 2, if we want to give kind of a formula or a way to describe the formula, then what I need to do is specify sigma of 1, sigma of 2, sigma of 3, and notice each one of those. Sigma of 1, it's some number. Sigma of 2, it's some number. Sigma of 3, and so on. So to describe sigma, we need to know sigma of 1, sigma of 2, up through sigma of n. And the way we're going to do this is we're going to use a 2 by n matrix. So we do this, we specify, or we describe, depict, how to depict. We depict this as a 2 by n matrix as follows. So we write sigma equals, in the top we'll do 1, 2, 3, dot, 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 all the way to n. Below 1, we will write sigma of 1. Below 2, we'll write sigma of 2. I've made it a little too crowded here. So we'll have a sigma of 1 and a sigma of 2 and a sigma of 3 all the way to sigma of n. All right. So, yeah, for example, so consider sigma in S6 defined by sigma is equal to, so 1, 2, 3, 4, 5, 6, 2, 1, 6, 5, 3, and 4. So what does that mean, right? How do you interpret this? So interpretation, sigma of 1 equals 2. Sigma of 2 equals 1. Sigma of, hopefully you can see the sigma of 4 equals 5. sigma, I'll do one more, sigma of 6 equals 4. You can figure out the other one. Sigma of 3 equals 6. Sigma of, who else? Sigma of 5 equals 3. Okay, so it's sort of a shorthand rather than writing out the formula. Sigma of 1 equals 2, sigma of 2 equals 1, sigma of 3 equals 6, and so on. That takes care of that with this sort of shorthand notation. So, for example, let's do another example. Okay, so once again, we'll be in S6. So let's let sigma be 1, 2, 3, 4, 5, 6, and then we're going to go 4, 2, 5, 6, 1, 3. Tau is going to be 1, 2, 3, 4, 5, 6, and then we're going to have 2, 1, 4, 3, 6, 5. And then I want to do a few computations. So part A, I'd like to represent the identity function in S6. That, by the way, has nothing to do with these sigmas and taus. But then part B, let's represent sigma inverse. And then part C, let's represent sigma tau and tau sigma. Oh, tau. Okay, so 3 different parts to this problem. For part A, let's see, the identity takes every element to itself, and so the identity should have matching rows, right? So 1, 2, 3, 4, 5, 6. Okay, so next we want to do sigma inverse, and so let's see. Part B, sigma inverse. So start off with a 1, 2, 3, 4, 5, 6. Okay, now how does this work? Well, sigma inverse, right? Remember, an inverse is supposed to be like sort of a descrambling machine. So sigma puts 1, it sends 1 to 4, which means that sigma inverse should send 4 back to 1. Sorry, I got something on my tooth here. Okay, sorry. Sigma sends 2 to 2, which means that sigma inverse should send 2 to 2. Sigma sends 3 to 5, so 5 should go to 3. 4 goes to 6, which means 6 needs to go to 4. And then, what am I missing? 6 goes to 3, which means that 3 needs to go to 6. Oh, and 5 goes to 1, so 1 needs to go to 5. Okay, so there's the inverse. And then we're going to do the compositions. So remember, composition is the one place in math, or one of the few places in math, where we have to read right to left. So when we do sigma tau, that means that you do tau first, then sigma. Okay, so for 1, tau of 1 equals 2. Sigma of 2 equals 2, so sigma tau of 1 equals 2. Tau of 2 equals 1. So we do tau first, we get a 1, and then 1 goes to 4. Do tau to 3, 3 goes to 4, which goes to 6. 4 goes to 3, which goes to 5. 5 goes to 6, which goes to 3. And then I shouldn't even have to look over there since it's a bijection. I've got to see all the numbers 1 through 6, which means 1's got to be there. But let's just check to make sure 6 goes to 5, which goes to 1. And now when we do it in the reverse order, so now I'm going to do tau sigma. So first, let's see, sigma. So now we're going to do sigma first, then tau. So sigma sends 1 to 4, 4 goes to 3. So 1 goes to 3. Sigma sends 2 to 2, and then do tau, we get a 1. 3 goes to 4, which goes to 6. 4 goes to 3, which goes to 5. 5 goes to 6, which goes to 3. Oh, I did that backwards. Oh, shoot. I feel like I was doing things backwards. Let me just start over so I don't keep a mistake on the board. I think I kind of lost track of what I was doing. I need to do sigmas first. So sigma sends 1 to 4, which goes to 3. Do sigma first. 2 goes to 2, which goes to 1. Sigma first. 3 goes to 5, which goes to 6. 4 goes to 6, which goes to 5. 5 goes to 1, which goes to 2. 6 goes to 3, which goes to 4. Okay, so there's some computations. And I guess one thing we should notice, so let's just say here, note, sigma tau is not equal to tau sigma. Those elements do not commute. And it actually turns out that this is true in general. So we'll just say fact. If n is greater than or equal to 3, then S sub n is not abelian. And the reason, in general, functions do not commute. Function composition is not commutative in general. Just checking the time here. Okay. So I'm going to do an example now. And what I want to do is take I need an n-gon. So let's give a symbol here. Let's let x sub n be the regular n-gon, just in the plane. A rigid transformation of x sub n. Now, what I mean by rigid is, so we're going to have this n-gon positioned in the plane. Think of the plane as being here horizontally, and we have our n-gon sitting there. A rigid transformation means that we pick it up, flip it around, do whatever you want, but when we put it back, it has to match the outline that it originally occupied, the space that it originally occupied. A rigid transformation of xn is a symmetry of x sub n. I'm going to just draw it. I'm going to just draw a regular foregon. All right, but we can do this in general. So imagine that you have a square, right? That's a regular foregon. How many different ways are there to pick this object up flop it around, and put it back where it was. And you know, I want to label my my vertices also. So there's going to be a 1, a 2, a 3, and a 4, just going around counterclockwise. Now let's see, what could we do? Well, one thing we could do is flip it vertically. We could also flip it horizontally, and we could flip it about a couple of diagonal axes also. So there's 4 different symmetries of x sub 4. What else do we have? Oh, we could rotate. And rotating various clicks, right? 90 degree, 180, 270, and 360, and then you start repeating yourself. So there are 4 reflections, those are flips about various axes, and there are 4 rotations, and we usually just consider the 0 degree rotation as one of them. That's the same as the 360 degree rotation. So let's give these some names here. So, well, for example, let's call this one mu1. Now, by labeling these, we can use our matrix notation to describe this particular symmetry. Because what happens if we do a symmetry of the foregone right here? What does it do? It permutes the vertices, and we label these vertices, right? So it corresponds to a permutation of the numbers 1, 2, 3, and 4. Right? So, for example, mu1 can be represented as the matrix 1, 2, 3, 4. And then, so let's see what happens. 1 goes to 2, and 2 goes to 1. 3 goes to 4, and 4 goes to 3. So it interchanges the top and the bottom vertices. The 90 degree, so let's say the 90 degree counterclockwise, so CCL rotation is, do I want to give it a symbol? Yeah, I'm going to call that rho sub 1. Rho, that's the, so that's a Greek letter, rho right there. So if we go counterclockwise, then 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. So this idea right here, what is this showing? We can think of the set of symmetries as sitting inside the symmetric group. Right? So let's let Dn be the set of symmetries of x sub n. Now, what's the size? Well, in general, what you're going to have is you will have n axes of symmetry, right? N axes where you can flip about. And you will also have n rotations, right? Taking the vertices 1, 1, 2, 3. The vertex can rotate until it gets all the way back around, and there are n vertices. And so there are n reflections and n rotations. So the total number of symmetries is 2n. So the cardinality, in fact, we're going to show that it's a group in just in a second. And so the order of this group is going to be the order of the group Dn is going to be 2n. Right, but officially I can't call it, can't say order, I'd have to say cardinality right now, because we don't know, we haven't proved that it's a group. So let's see, we can view Dn as sitting inside subset of S sub n. Right? By labeling those vertices, right, that gives us a way to view Dn as sitting inside. Now, clearly, Dn is closed under products, where remember products is composition, so a symmetry is a permutation of the numbers 1 through n, right? And so if you do two symmetries, you get a symmetry. Also, the inverse of a reflection, just reflect again, which is the same as unreflecting. And if you rotate a certain number of degrees, just rotate back, right? So it's closed under inverses also. It's also obviously non-empty. And so what we just did is we have dn, so you can say therefore, dn is a subgroup of S of n. This has a name. It's called the dihedral group. So dn, d sub n, is the nth dihedral group. Let's do, let's see. Yeah. Let's study D3, right? That's the group of symmetries of the triangle now. Now let's just let's try to write down all the elements and get a feel for what's going on there. So, let's see. So this will be kind of a lengthy example where we look at D3. And so let's draw the picture. And so let's see how I want to label this. Let's label the vertices 1, 2, and 3 like that. There are going to be 3 axes of symmetry. So there's that flip, there's that flip, and there's that flip. And I want to call them, and I need to be consistent here. So this one right here will be mu1. The next one, oh, right. Yeah, so it extends from vertex 2, so this is going to be mu2, and then this will be, that flip right there will be mu3. And then the rotations are going to be row 0, that's the 0 degree reflection, counterclockwise. Row 1 is going to be 120, and then row 2 will be 240. So let's write them down, who each of the elements are. So we've got the rotations. And so row 0, that's the 0 degree reflection. That will be 1, 2, 3, 1, 2, 3. That's the identity. And then I'm going to call it row 1. That's going to be counterclockwise rotation through 120 degrees. So that will be 2, 3, 1. So this is 120 degree counterclockwise CCL rotation. And then one more row sub 2, so that's going to be the 240 degree rotation. 1, 2, 3, and then if we go 240, 1 goes to 3, 2 goes to 1, and 3 goes to 2. So that's 240 degree counterclockwise rotation. Then, sorry, I hate being so crowded here, but there are going to be now 3 flips. So these are the reflections. And so what's that going to be? Mu1 will be the reflection 1, 2, 3. And let's see, if I reflect about this line, it leaves 1 fixed and it interchanges 2 and 3. Mu2 will be, so mu2 leaves as 2 fixed and it interchanges 1 and 3. And then mu3, 1, 2, 3, 2, 1, 3. Okay, so I've now written, sorry it's a little sloppy here, but I've written down in order my 3 rotations, then my 3 reflections, for a total of 6 elements, which is exactly what we knew. D3 has 2 times 3, which equals 6 elements. Now, here's one interesting thing. We know that D3 is a subgroup of S3. The order of D3 is 2 times 3, which is 6. The order of S3 is 3 factorial, which is also 6. So what that tells us is, so conclusion, S3 is equal to D3. They're exactly the same group. That doesn't happen in general. As soon as you get to S4 versus D4, S4 is definitely bigger than D4, and so on. Right, so it only happens in this case when n equals 3. Yeah, let's do a little bit more here. And this, well, it's kind of a, I'm going to do some of it, like actually work it out. What I want to do is I'd like to write down the Cayley table for D3. So we're going to have row 0, row 1, row 2, mu1, mu2, mu3. Let's space it out a little bit more. mu1, mu2, mu3. Row 0, row 1, row 2, mu1, mu2, mu3. So let's do a few of these, and then I'll fill in the blanks, and you can just check. I have them all written down here. So first of all, row 0, that's the identity. So this first row here would be row 0, row 1, row 2, mu1, mu2, mu3. Same thing with the first column here, row 1, row 2, row mu1, mu2, mu3. Now let's see. If I do, so let's figure out who this one is right here. Row 1 times row 1. What does that mean? It means rotate 120 and then rotate 120 again. So row 1 times row 1 is row 2, right? It's the 240-degree rotation. Row 2 times row 1, what that means is rotate 240 and then rotate another 120. That's 360. So that gives us row 0. And let's fill in a couple of them here more. Row 1 times row 2 will definitely be row 0. Row 2 times row 2, that's going to be 240 and then another 240, which is the same as 120. So that's row 1. Right, so we filled in that little box there. What else? So let's do a couple of these. Oh, you know what? Let's do the products here. So mu1 times mu1. If you reflect and then reflect again doing the same reflection, right, what do? You get back to where you started. So mu1 times mu1 is row 0. Mu2 squared is row 0. Mu3 squared is row 0, right? So that takes care of that diagonal piece there. And then let's do 1 or 2 of these, and then I'll just tell you who the rest are. So maybe let's do this one right here. So that's row 1 times mu2. Row 1 times mu2. Okay, so let's see if we can just do it geometrically rather than writing everything out. So I need to reflect, and I want to see what happens to each of the vertices. So 1, what happens to 1? If we do reflection about, so we're doing mu2, so that takes it to 3, and then we reflect, 1 goes to 1. And then what happens to 2? If we do mu2, nothing, and then it goes to 3. So 2 goes to 3. And then 3 has to go to 2. And so who is that? Row 1 times mu2 is, who is it? It's 1, 3, 2, so it's mu1. And so you can do this all the way through. Let me fill it in and I'll let you check these. In fact, maybe I'll leave a few blank. So let me just do a few more so you can see what's going on. So that's a mu3, mu2. Right here, this will be row 1, row 2. Let me write in a few more here. Mu2, this is mu1. No, that's mu3. And then mu2 times row 2 is mu1. Down here we'll have mu1, mu2. Let me get out of the way. And let me fill in a couple more. I'll fill in that bottom row there. Row 1, row 2. I think we can pretty much figure out what things are at some point, but let's see. So this one is going to be, this is going to be mu1 right there, which means this one has to be row 1. So let me leave these 5 blanks, and you should go through and actually compute these. Oh, well, you know what? This just, I already finished this one off. That one has to be row 2. And then that means that, oh man, well, okay. Just do it geometrically. Test to see if you can figure out and make sure that they agree. Like now I've noticed, okay, these are determined, and so are these. I was trying to be, well, anyways, that's that. Oh, there's some subgroups also. So let's write down the subgroup lattice, and we'll finish with that. Finding the subgroup lattice in general is tough, right? We're able to do it for cyclic groups fairly easy because we have, first of all, we know that all subgroups are cyclic, and so all we do is look at all the subgroups generated by all the elements and figure out which ones are match, and then just draw the picture. It's a little tougher with dihedral groups. So subgroups. Let's see. It turns out that all these subgroups of D3 are cyclic. This is not usually the case, right? But in this case, what we get is, so there's the subgroup generated by mu1, and so that's going to be row 0 and mu1. There's the subgroup generated by mu2, that's row 0 and mu2. There's the subgroup generated by mu3, which is identity and mu3. Then there's the subgroup generated by row 1, which consists of the identity, row 1, and row 2, and it turns out that that's exactly the same as the cyclic subgroup generated by row 2. There's also the trivial subgroup and the whole group, and that's it, right? So this is not typical, but in this case, all of the proper subgroups are cyclic. D3 itself is not cyclic, though. Right? We just wrote down, in fact, you can see that. We wrote down all the cyclic subgroups right here, and you don't see D3. You don't see any element that has order 6. So D3 is not cyclic. So the subgroup lattice will look like this. There is no overlap at all. mu1, mu2, mu3, and subgroup generated by row 1. And then the trivial subgroup, which in this case just consists of row 0, sits below. In your book, D4, both the Cayley table and the subgroup lattice are given. So I'm just going to say, we'll finish it here. So see the text for Cayley table and table and lattice of D sub 4. It's definitely more complicated, especially the subgroup lattice, right? But some of your homework questions for the following, I guess it'll be homework 3, will ask you to say stuff about, or make use of the Cayley table or the subgroup lattice. So that's a good place to stop. We will see you next time.